Today's lesson we look at tangents a little bit more specifically, as 9.2 is just about those types of lines. There are a few theorems and ideas that we'll talk about. The first being that if a line is tangent to a circle, the line is perpendicular to the radius at the point of tangency. So the point of tangency being the point where the tangent meets the circle, and the radius drawn from the center point is perpendicular to that. That is true no matter where the point of tangency is and no matter where the radius is drawn. One of the corollaries states that if you have a tangent or two tangents going from the same point, those two tangents are congruent, almost like an isosceles triangle. Looking at the converse of theorem 9.1, if a line in a plane of a circle is perpendicular to a radius at its outer endpoint, then the line is tangent. So now we can prove tangency based on the radius of the circle and the line being perpendicular. Now, does that mean that every single line that's perpendicular to the radius is its tangent? No, I'm sure you can see a lot of lines that you could draw through that point that could also be perpendicular. But remember, it also only touches the circle in one spot. Hit pause and answer questions 1 through 8 right now. There are lots of types of tangents that we can talk about, and one of the ways that tangents are seen is when a circle is inscribed in the polygon, and the polygon is circumscribed about the circle. In last lesson, I said that a polygon can be inscribed in a circle if all the vertices are touching the circle. Well, a circle can be inscribed in a polygon if all the sides are tangent to the circle. Notice here we have a pentagon. All sides appear to be tangent to the circle, therefore the circle would be considered inscribed with it. Polygon would be considered circumscribed about the circle. Same thing here for the triangle. And we did talk about a couple of things in lesson 10.3 regarding how circles are created from triangles inside, but depending on whether it's the median or the altitudes or the perpendicular bisectors that are intersecting. Two circles can have a common tangent as long as they're coplanar, and the line obviously is tangent to both. The two common tangents are either internal or external. The way that's determined is by connecting an imaginary line or an auxiliary line to the two center points of the circle and then drawing that tangent that is common between the two circles. If the line that's tangent between the two circles intersects the imaginary or auxiliary line, it is considered to be a common internal tangent, and if the line never touches the segment between the two centers of the circles, then the tangent is considered to be external. Circles can also be tangent to one another. Tangent circles share the same point, share the same tangent at the point of tangency, and therefore we have circles that have the red line as the tangent, and the point of tangency is right in that area as well. If the two circles are on the outside of the tangent, they are externally tangent to each other. And if the two circles share the same tangent, but one circle is inside the other, it would be considered internally tangent. Now, this is different than the last slide because remember, we're talking about the tangent being the tangent line, whereas the circles are tangent to each other, basically intersecting the same tangent at the same point of tangency. Here are some good examples of some commonly tangent circles. These would all be considered commonly externally tangent, unless you're talking about the entire circle on the outside, everything being on the inside of that. This is a good example of a set of circles that are internally tangent to each other. And one last one that you might see an example of in your homework or an example in class would be these commonly tangent circles. They could represent a radius or they could represent the diameter, and as you can see there's a lot of common tangents that are involved with this drawing. Hit pause and answer questions 9 through 14 now. Using theorem 9.2, which bases our idea of a tangent existing, our job here is to determine whether or not AB is the tangent to the circle. And using that information, the only way we know how to do that at this point is to prove somehow that angle A is a 90-degree angle. So use what you know about 90-degree angles and determine whether or not AB is a tangent. You should have said that the radius is also 12 based on this radius here, and based on the fact that the Pythagorean theorem tells us a 90-degree angle exists, we can say that AB is a tangent. Take a look at this one here. Is AB a tangent here? Using the Pythagorean theorem here, we know that 6.6 squared plus 11 squared does not equal 13 squared, and therefore we can say that AB is not tangent. Now our job is to find the length of the segment based on the information we know. The idea that we have a tangent existing is the only thing that gives us that. So we would go back to the basis for this whole lesson, which is that if you have a line that is tangent, it is perpendicular to the radius at the point of tangency. Therefore, find out whether what the value of the diameter of the circle is. Using the Pythagorean theorem, you should have found that the value of that is 7.5. Try this one. Now you're trying to find the tangent. You should have said that 1.5 was also the radius on this side here. Using that Pythagorean theorem, you now have the question mark being the value of 2. Hit pause and answer questions 15 through 17 and bring any questions you have for class tomorrow.